with a vision to advance science and industry through photonic technologies. And the title is Choose Your Tools Wisely. And we learn what that will mean. And I'm looking for Sebastian. There he is, Sebastian Baer, please. He's application engineer at Hamamatsu, and I'm curious what kind of tools you will recommend. Please give him an applause.
Thank you very much. Is this one the... All right, now from a very strategic and general talk to a more specific and technology-oriented talk. I want to talk about cameras and photon counting cameras in general. But first of all, for those who don't know Hamamatsu, we're a company that manufactures general detectors, from vacuum tubes to silicon detectors to full-fledged cameras or sensing modules. We were founded in Japan, and still our headquarters are in Japan, and we've been around for more than 7 decades. We have a lot of research and development and production facilities in Japan mostly, and we reinvest a lot of our revenue back into R&D to be always on the top of technology. We have 3 direct Nobel Prize contributions across the time. I think it was 2 times neutrino research and 1 times the Higgs boson. A little bit more than 5,000 employees and a lot of products. Our headquarters, as mentioned, in Japan, in the city called Hamamatsu, but we're located all over the world with a couple of thousand products. We do value a lot personal interaction. So if you have an issue and need to detect light in some way or another, it's always better to have some discussions with us than to search our webpage. All right. The support network is pretty dense in Europe, so we can always be close by. Back to the general technological topic about cameras. First of all, I'd like to talk about my personal motivation and the latest camera model which motivated this research. Then a little bit in detail about how do we resolve photon numbers within individual pixels, and then finally benchmark that one against standard single photon counting techniques. So first of all, why did I bother to do some kind of photon counting benchmarking? Well, of course, coming from a company that was motivated by a product which we released around 2 years ago, the Orca Quest. We have it on our booth directly in your back. And the key features of these cameras are extremely low readout noise, which directly translates into the so-called photon number resolving capability. So how does that work in detail? Consider some input signal, say 0 photons. Then the output probability of this camera with this specific noise would give us this distribution, which is pretty narrow, and opposed to other cameras which potentially feature some kind of electron multiplication, this distribution is independent of the input light level. So if we input 1 photon, 2 photons, or 3 photons, we always get the same distribution, and we see a certain modulation based on the number of incident photons within each pixel. And well, this is simply calculated via Excel. It's pretty cool that we can also see that directly out of the camera. So I took one of our cameras and placed a lot of ND filters in front of the objectives and took an image of my coffee mug. And on the right-hand side here, you see actually the histogram is not continuous anymore as with standard cameras, but it is pretty strongly modulated. And of course, do I have a pointer over here? No, I don't have a pointer, but the first peak over here corresponds to all the pixels who are completely dark. The second peak to the ones containing 1 photon, 2 photons, and so on and so forth. And the way to achieve the photon numbers is then pretty simply by drawing multiple thresholds. So we define that everything below 0.5 electrons is absolute darkness. Everything within the second peak contains 1 photon, 2 photons, and so on and so forth. And that goes up theoretically unlimited. We see there's still a small overlap, but that is not negligible, but easily accountable, let's put it that way. So the wrong counts or the wrong accounted for counts are pretty much known. They will be the ones out of the bounds, which are below the half electron marks within the probability distributions. And we can easily account for those and then deduct the expected number of errors which we would get, or the numbers of false classifications of our photon numbers. And our design goal was actually to achieve a readout noise below 0.3 electrons to provide a precision of more than 90%. And in the end, we reached 0.27 electrons, and everybody was quite happy and said, this called for a new name. We're going to name this quantitative CMOS because this is actually the first time that we do have a true digital camera, a true camera that can determine the number of photoelectrons. So yeah, everybody in the company was extremely proud, and we went around and told everybody about that. And people were just like, yeah, you know, that's great, but we've been counting single photons for more than 4 decades. Which is essentially true. I think Hamamatsu released the first single photon counting camera in 1982, which was before I joined the company for obvious reasons. But there are certain differences between photon number resolving and single photon counting. On the one hand, if we go for the general concepts, single photon counting in itself is a binary decision, meaning based on the technology, we can determine the difference between absolute darkness, 0, or larger than 0. If we reduce our signal extremely so that we can assume that we only have single events present, then we can rescale that to 0 or 1 and call that single photon counting. Photon number resolving, on the other hand, gives us the same performance, but with intensity resolution, meaning the output can be 0, 1, 2, 3, up till any arbitrary number. So from that perspective, as I already said, it is single photon counting performance with intensity resolution. Theoretically superior to single photon counting, but we're talking about different technologies here. So in the most common sense, and the ones most people are familiar here with, is likely single photon counting with PMTs or silicon spuds, and photon number resolving more with those cryogenic sensors. But since we're talking about cameras here, I would like to draw the attention to either the photon number resolving QCMOS camera or the often used EMCCDs. So how do we compare both of them? Doing that experimentally at such low photon regimes poses some difficulties and some straight comparisons, so I went to simulate everything because luckily Hamamatsu manufactures both cameras and I had detailed information about both of them. So the idea is that I simulate uniform illumination and use the same seed images for both camera models and then perform the single photon counting and the photon number resolving operation. That kind of eliminates any bias towards any cameras and gives me a fair comparison in different scenarios. So in the end, it looked like that. On the left-hand side, we had our seed image with some photon imposed and the QCMOS image and the EMCCD image, putting that through the photon number resolving and the single photon counting thresholding operations, and we received some outputs which we then can compare and benchmark. Now, a key question when performing those benchmarking operations is which metric to choose. Initially, I was very naive and thought I might use, oh, sorry, I was a little bit ahead of my slides. First of all, we used the model parameters which were directly derived from specific models of those cameras. And for one parameter, which is quite important, is we used the single photon counting threshold of 5 times the readout noise of an EMCCD camera, namely 250 electrons. Regarding the metric, we could use SNR, but you quickly run into issues there since single photon counting images tend to saturate rather quickly at 1. So we could compare the images because we have the ground truth available. However, in the most exciting scenarios, most of the image will be dark. So the image will be highly similar and the differences might be masked by that. So in the end, I decided to go for the fraction of true non-zero pixel plus the efficiency of how many photons were detected. That gives me 2 separate metrics, and the other one is the Jakar index, which combines both of those things, which is basically just the intersection over union, all the simulated photons plus the dark counts as the reference, and all the detected photons as the truth. All right, and this in itself is directly the output. So we see in blue the photon number resolving performance, and in orange the single photon counting performance across different signal levels in photons per pixel per frame. So what we see here is that in single photon counting, on the left-hand side, on the lower intensity limit, we have some limit caused by clock-induced charges or dark counts. And on the right-hand image, around 1 photon per pixel per frame, that is, of course, limited by coincidence, because single photon counting can never reach above 1. With photon number resolving, we see that the left-hand side limit, the lower intensity limit, will be caused by the residual noise, which indicates some dark counts, whereas the right-hand side limit initially surprised me quite much, because we expect photon number resolution to go on to infinity, at least conceptually. Thinking about it in detail, it has to do with my metric and the general performance of photon counting approaches. It is caused by the efficiency. We always have to consider that in photon counting approaches, we never really count photons. We always count photoelectrons. So, meaning we never know what we are missing, except we have an efficiency of 100%, and I'm not really sure that there is such a process in physics. So in the end, the QE acts on each photon individually, and that results that, for example, with 10 impinging photons on a pixel and a quantum efficiency of 90%, we don't have a 90% of generating 10 photoelectrons, but rather a 35% chance of generating 10 photoelectrons. It is in the end a binomial process. And looking at the graph, it counts up quite nicely that we end up with 10 photons at 35%. Now, single photon counting also suffers from this issue, but it's masked by coincidence. Since we are working in simulations, I can simply ignore quantum efficiency or assume perfect quantum efficiency, and here we see the expected behavior that photon number resolution goes up towards infinity, and the efficiency also is higher since we don't have the strict threshold losses as in single photon counting operations. If we're looking at the Jacquard index, we don't need to ignore quantum efficiency because the Jacquard index accounts for each photon individually. So in the end, that basically concludes most of my talk and all of the results. In the end, we can see that the overlap between photon number resolution and single photon counting is on the order of 0.1 photons per pixel per frame on average. Meaning, conceptually, as I already mentioned, photon number resolving is superior to single photon counting. In the current implementation, I always say, when you're sure that you only have single photons available, it's better to use single photon counting. If you might need some intensity resolution, it might be better to use photon number resolving. What is also to consider is that the limitation of single photon counting is conceptual by design, whereas the limitations of photon number resolving with a CMOS chip at the moment is a technological challenge which might be solved in the future. Also with photon number resolving approaches, we get direct access to the photon statistics, which of course is interesting once you're dealing with non-standard photon statistics, just like in biphoton approaches with SPDC beams. Total efficiency always has to be considered. And finally, we could improve both techniques a little bit by managing the thresholds a little bit better, as I've shown earlier on. And with this, I'd like to thank you very much, and I'm open for questions.
Yes, questions. I was following. I would have to say I'm impressed. I learned a lot of things. Do we have questions in the audience over there, please? You get a mic.
Yeah. Thanks for this very nice talk. So, of course, we know some advantage and disadvantage of the single photon detector and also this photon number resolving. But the problem, I think one problem is the response time. So, like, do you have any comment? Like, what's usually the better? Because from my knowledge, single photon counting, the response time is much faster than like this camera stuff. So, yeah.
Absolutely. I mean, it's like I deliberately compared two cameras and not a point detector because the speed is a limiting factor. We're still talking about cameras which are basically massively parallel light intensity measurements. So to give you a short answer, the QCMOS camera runs at 5 frames per second, full frame with 10 megapixels, meaning you get a slow speed but a massively parallel measurement. So it can't compete with SPATs or PMTs for quantum communication approaches at the moment, but therefore you wouldn't use a camera in any case. Sorry.
Can we have the mic one more? 1 second.
Then how about a single photon detector array?
It's the EMCCD that runs at 70 frames per second in that mode I presented, but with only 0.25 megapixels. So you have way less bandwidth from that perspective, but a higher speed.
The next question is like, do you work on this array?
Well, we are always working on improving our cameras, but there's not that much I would like to present at this time in this place.
But maybe, Sebastian, you guys can follow up and as in one-on-one when you leave the stage, because there are good questions. And I also have to ask you now to actually leave the stage because we're running out of time.
Oh, I'm very sorry.
No, Sebastian, thank you so much. Please give it an applause.